fortune. I'm not sure how many of you know her. She's one of the most influential women here in Great Britain. If you don't know her, please take her. And she is also extremely humble, and honestly, we are also extremely humbled to have her as our board of director. As I mentioned earlier, we have had 3 conferences here at Southern University. We had another 2 at Queen Mary University. It's only because due to her selfless effort and unlimited support. Could I therefore kindly ask you to give her a round of applause?
Hello everyone. It's my huge pleasure to introduce the guest speaker. But just before I do that, I'd like you to remember the guest speaker we had the last time at Queen Mary, Lord Mawson. If you remember, he was the priest who was sent into the East End, decided there was no point having a church where the people were so poor. So his church became a nursery, a hairdresser, a coffee shop. And that started the regeneration of the East End, which is the only part of London where house prices are going up, which isn't such a good idea. But actually, the children, when he started, no one went into secondary, let alone higher education. Now, last year, 20% of the output from the East End went to Russell Group University, the university of their first choice. So what he did, he enthusiased everyone, and that led to excellent pitching, all right, which we had the next day. And we'll have pitching this afternoon, so I want you to go away after the talk and think about it. The outcome of that was lots of entrepreneur work, and the consequence is there's a huge women's cooperative in Cape Town now, there's one in Zimbabwe, there's one in Malawi, and one in Nigeria. Why women? It's a good idea if women are upskilled, employed, money to get paid for school fees. Remember, most of Africa you have to pay for school fees and bread on the table. So now it's a huge, huge pleasure. And I introduce our next speaker with great gratitude, excitement, and expectation. So you've all heard of Brian Cox, and he is amazing. To be a particle physicist and be able to engage the world, that's a huge thing. So, he's a fantastic scientist. He's FRS. He's had 2 prizes. He's a mega physicist. He's had a Kelvin Prize and a Michael Faraday Prize. He probably has more than I have heard of. He's an author of several books, and I would recommend reading them. The one I like best is The Quantum Universe, which I read again and again and again. And so if you get buy one for Christmas for anyone, go and have a look. I've done several. But that one is actually a really, really good read. Now, that doesn't actually make him one of us. He's a musician, which does. Okay, and if you want to go to a concert, do you still have a concert next year?
Oh, they're actually, next year, it's a speaking tour, so they're essentially cosmology lectures, although the cosmology lecture is in Wembley Arena in February, and then the O2 in September. So yeah.
If you go, because it will be very, very good. But what makes him one of us is he can raise aspiration. Now, my big thing, I've been in higher education here all my life, right? When I go back to Africa, the difference is there's aspiration in the kids, in their family, wanting things for them, education and health. And I there's no aspiration yet. Okay? He's fantastic at doing that. Because part of this regeneration of his kids in the East End doing so well. And then, if you remember, he came and gave a talk. And, you know, and so I'm a governor of one of these schools. They all wanted to be particle physicists. But the thing is, for the kids that never went into secondary education, you know, something like this, coming in and changing your life, right? And it was somebody like him who came into my life and was running around barefoot when I was 6, 7 years old, that made me persevere and get sent to England. So today I'm sure he is going to do that. And for somebody who has got the skills of both David Attenborough and Patrick Moore. So a few of you might not remember Patrick Moore, but when I was at school, he'd come on this television and he talked really, really fast. I mean, when I went home to Africa, I spent all my time lying down and watching the Milky Way. So today, I'm sure that we're going to raise your enthusiasm for the pitching this afternoon. So after this, don't have lunch. Sit down, think of what you're going to pitch, okay, and tell us. I'm going to give you a few 5-10 minutes, everyone, if you want to pitch. And from that will build our meeting in Ethiopia and then in Lesotho next year. Okay, so thank you very much for coming. Deeply humbled to have you here. And
I'm going to lower the light, which I think is that one. So that you can see these photographs, if that's okay. You don't need to see me, you can see the photographs. So I'm primarily going to talk about astronomy, cosmology, what we've learned about the evolution of the universe from the earliest times through to the present day, but also focus on our place in the universe. And cosmology, I think, is often described rightly, I think, as terrifying, because the size and scale of the universe and contemplating the size and scale does raise, I think, quite profound questions about what our place is, so what it means to be human. So those are the things I really want to focus on, but I wanted to just tell you a little bit about my connection with Ethiopia. So why am I here? Why am I connected with GKEN? The reason is that I visited the country for quite an extended period of time on 2 occasions to film, and found it welcoming and exciting and fascinating. And in fact, I think one of the reasons I was asked to be involved here with GKEN was because I always seem to say very nice things about the country when I'm on television. It was noticed. And that was genuine. We filmed there, of course, I think as many people do, because it is the cradle of humanity. And one of the themes that's always runs through my television programs, and will run through this talk, is the fact that what we're trying to do, think about the challenge that astronomy and cosmology delivers to us. It really is trying to make sense of the fact that we are very small and fragile things, living a temporary existence in an infinite universe that may well be around forever. And actually, even though we know there was such a thing as the Big Bang, may in fact have been around before that. So we may live in an eternal universe, and we certainly occupy a very small part of it. But what we found is that, or what we strongly suspect, is that structures like us, human beings, what the great physicist Richard Feynman called atoms that can contemplate atoms, the wonderful thing to be, may well be extremely rare in the universe. And that, I think, gives us great value. And if you think about that, so you think about the idea that consciousness, that thoughts, that humans are perhaps a very rare phenomenon across the universe, then this place, Ethiopia, becomes an extremely valuable place indeed, because it is the place where that arose, and that there is no doubt the Rift Valley of East Africa, as far as we can tell. So that's the reason that I often visit when filming these programs and trying to address these issues. So I just thought I'd show you a couple of photographs that I took during our filming trips before I get to the astronomy. And this is a photograph in the Highlands, just outside of Addis, when we were filming Gelada baboons, or Galana baboons, I don't know how to pronounce exactly. But if you haven't been there, they're quite a remarkable. So I should say a troop of animals that have a very sophisticated communication between the individuals and quite a sophisticated society, and live exclusively in the highlands of Ethiopia outside Addis. So we filmed there. And also, we just in the introduction about fixing forward too much. I just want to show you this because in the introduction we talked about the universality of inspiration and curiosity, and the fact that the aspiration and the ambition of children all over the world is the same. And I found this when we filmed in a small village, again just outside Addis, talked about human origins. But afterwards, we spent about 2 hours with the translators discussing astronomy, in fact, with all these children. So we had an impromptu lecture for a couple of hours, and it does tell you that raw material, the human curiosity that children, the raw material is present, of course, as you all know, in every country in the world. And I suppose the great challenge for humanity as a whole and our civilization is to make sure that those students who are absolutely as able and curious as any students that you'll meet anywhere in London or America or wherever have that opportunity and that sense of possibility to move through and become whatever they want to be, astronomers or whatever it is. And that's one of the reasons why I think that I haven't visited actually, but the Ethiopian Space Sciences Society opened the observatory just outside of Addis, or in Addis. And I want to see that because I think it's extremely valuable. If you read about it, I looked through actually some of the comments online about that project, and you'll see various comments. Some are what I would share, it's just a wonderful thing to do. But some of you always get those comments that, well, why would you be building telescopes in a country that needs other things, infrastructure and so on? But the answer is, of course, that it's inspiration and education are the way for countries to develop. And even though it's quite expensive in a sense, but just a few $1 million in another sense, I think the idea that you begin to build those things, which are the focus of dreams, the reason I became an astronomer and then a physicist and a particle physicist is partly because I visited observatories, in particular Jodrell Bank Observatory near Manchester, where I grew up. So I think those projects, those inspirational projects, are absolutely vital so that children like this can aspire to become whatever they want to be. So I had a wonderful time in this village. Then I just went through actually, because my clicker's not working very well, so there we go. At the other end of the spectrum in Ethiopia, the first time I went there actually, we visited this place and filmed at this place, which is Evaporate in the north, which is, in my memory, one of the most spectacular places I've ever visited. At the time, one of the most difficult places I've ever visited. It's very difficult to get there, as many of you may know. Very, very hot in the Danakil Depression, above 40 degrees every day when we were there. So that was one of the places that, in my memory, I always say this is one of my favourite places to be. But at the time, actually, it's probably one of my least favourite places to be. But it is truly spectacular. And then finally, just one of the, I said that I tend to say rather sort of heartfelt nice things about the country. This was just a shot at the end of a programme which addressed all these issues in a series called Human Universe. And we chose to film the end of the programme and the reflections on the value of humanity overlooking Addis. And this is just one of the shots, and it's one of those memorable pieces of camera that I remember doing. So that's my connection to Ethiopia. But as I said, primarily I want to talk about astronomy and astrophysics. You can't see me now, you just have to look at the pictures. When we talk about cosmology, the large-scale evolution of the universe, we're not really talking about small things such as planets. Now, planets seem vast to us, but even planets and solar systems and galaxies are relatively small objects when we're talking about the large-scale evolution of the universe. I thought I'd just, on the way out to the galaxies, step out through our solar system. I just wanted to show you a couple of photographs from the last year or two in space exploration, because space exploration is progressing at a rate that I think even I didn't imagine when I first got interested in the 1970s. The sheer quality of the data that we're getting back from the solar system is allowing us to begin to answer some of these questions, or at least begin to see the route to an answer. Some of the questions such as, how likely is it that life exists beyond Earth? It's true to say, and it's worth reflecting on, and say again, that this is the only place we know of in the universe currently where there is any life, even microbes. We don't know for sure how likely it is that even microbial life will arise on a planet. And if you think about it, the origin of life is, what is it? We know that life began around 3.8 billion years ago, or certainly life was present about 3.8 billion years ago on this planet. This planet is only 4.5 billion years old. When it formed, there was no life in it. So life must be chemistry, and it must be the transition somehow from geochemistry to biochemistry. An expression, in that sense, you can consider life as the expression of an active world, or the consequence of an active geological world. So one of the reasons, one of the prime reasons I would say that we explore the solar system is to see whether there's anywhere else in our backyard that transition may have happened, transition from geochemistry on a young active planet to biochemistry. But also it's worth noting that if you look at this picture, the most remarkable thing is not the blue planet or the Earth itself, I think, but the civilization that is clearly visible on the planet. And that echoes what I said at the start of this talk, that actually humanity, the existence of these curious collections of atoms that can contemplate atoms, is a thing to be valued across our universe. We don't know where else that's happening. If we start to step out, I said that I just wanted to show you a couple of pictures before we get into the physics. There's a spacecraft in orbit around Jupiter at the moment, which is trying to understand, its job really is to understand the origin of the planet, Jupiter. So how did Jupiter evolve? What is the cross-section through the planet? What does Jupiter's core look like? Jupiter played a key role in the origin and evolution, certainly, of the solar system. Without Jupiter, it is certainly fair to say Earth would be a very different place to the way that it is now. So if you follow the formation of the planets from a cloud of gas and dust around the young sun, then Jupiter plays a key role in determining which planets, even the size of the planet. If you think that the fact that Mars is a smaller planet than Earth may well have been caused in the early history of the solar system by the influence of Jupiter on the planets further in. That's because it's very large, very massive. It subdominates the mass of the solar system other than the mass that's contained in the Sun. Well, this is a spectacular picture taken by the Juno spacecraft, because Juno orbits around the poles of Jupiter rather than the equator. So all the pictures we see from Earth-based telescopes of Jupiter tend to be this red and orange world with the great red spots and so on. But when you start to orbit over the poles, you see a very different planet with these blues and different chemistry at the poles, just because of the different, well, in part we don't fully understand, but certainly part of the fact that the solar heating is different, the clouds chemistry is different, feeding into this. And when you look at some of the photographs, these things look like impressionist paintings in a sense, but they're detailed photographs taken by the Juno spacecraft as it tries to understand the meteorology and the chemistry of Jupiter's very turbulent atmosphere. You see there. And more, again, from Juno, but a more familiar picture of the Great Red Spot. Just saying the scale, I mentioned that Earth is a small place, and we're a very small collection of atoms on the Earth. Small, even in the context of the solar system, you can fit about 2.5 to 3 Earths across the Great Red Spot, just to set the scale. And that's a storm system, which was certainly there when Galileo first saw it, so it's been about 350 years or something like that. It's getting smaller, so it's shrinking before our very eyes, so it won't last forever. But it's a very long-lived and very large storm system on the planet. Saturn, we've had a spacecraft which ended its mission last year called Cassini, out there for many years now, taking quite remarkable pictures of Saturn. The rings obviously it's the jewel of the solar system, many people describe Saturn as. The rings are interesting because we think now that they're very young indeed. In fact, we think that they could only be tens of millions of years old and were probably created by the destruction of the moon, that essentially because of gravitational interactions with the other moons wandered too close to the planet and the moon disintegrated into this ring of water ice, primarily water ice around the planet. So it's quite possible that in the time of the dinosaurs, then these rings would not have been there. And it's quite possible that they won't be there for very long. So this most spectacular site of the solar system is not an eternal site. It's probably a fleeting phenomenon around the planet, and the rings won't be there forever. We're fortunate in that sense. As I said, they're water ice, they're very delicate. They're only about 10 meters thick. So in fact, they just about fit inside this auditorium, edge on. But then of course they're vast and hundreds of thousands of kilometers in diameter as they surround the gas giants. And every picture pretty much that we've seen that you look at the rings look like they're some kind of artist's impression of some alien world. But these are not, these are photographs taken by the Cassini spacecraft. The delicate structure in there is caused by the moons. Saturn has over 60 large moons and countless hundreds of smaller moons. And it's the gravitational field, called the complex field, created by those moons orbiting around the planet, that you're seeing there. Now, I've got a friend actually who works on a mission who said that it's as if some sort of benevolent deity decided that what they do is sprinkle ice, snowflakes, over the gravitational field of Saturn to reveal it. In the same way that you get iron filings and put them around a magnet, you see the magnetic field. This is snowflakes, a sort of particle device sprinkled over the gravitational field caused by the planet and its many, many moons. And I talked about the delicacy. I mean, this is a photograph. We have to remember a billion kilometers away, and you see the delicacy of the rings in these photographs. The interesting thing, though, about Saturn, which, and it's a lesson here, I think, we only found that it was the most interesting thing when we went there and explored, turned out to be the moons. Now, before we went to places like Saturn and Jupiter, I think the idea of a moon was coloured by our experience of our own moon, which is a geologically inactive, inert place. It's very beautiful, it's a remarkable thing to visit, but it's a dead world. And I think that was really the paradigm in solar system exploration until we went there. But when we got to the moons of the outer gas giants, we found that was not the case. And this is a photograph of a very small moon, actually, smaller than the United Kingdom, so it's smaller than our little island, called Enceladus. This is a photograph of it above the ring plane, and you see it's in crescent. But you can also see there's some sort of smudge off the bottom darkened limb of the moon, which is a complete surprise. And so the Cassini spacecraft started doing close flybys of this moon, taking pictures like this. We saw an interesting surface with great canyons in the surface, where these sort of light blue or turquoise canyons, which became known as the tiger stripes. And when we did close flybys over those, we saw the origin of that smudge, the smudginess, which is eruptions of water ice coming up from the surface. So what we're fairly sure is happening on this very small moon and in the frozen outer reaches of the solar system is that there are lakes of liquid below the surface, liquid water, which are bursting up through the surface because we think there's geological activity in the core. So we think that there are structures called hydrothermal vent systems in liquid water lakes below the surface, which are driving the water out through the crust and then out in space, where it immediately becomes ice crystals and actually forms an outer ring around the planet. That's interesting, because if we go back to what I mentioned about the origin of life on Earth 3.84 billion years ago or so, one of the most popular theories, widely supported theories, is that it may have begun in hydrothermal vent systems on the floors of the oceans of ancient Earth. Because all the chemistry of life, all the driving forces for building complex carbon chemistry are present in hydrothermal vent systems. And so it is at least possible, and some space scientists think that it may be so possible that we should send a spacecraft equipped to look for life. It may be possible that there's life in the oceans or the subsurface lakes of Enceladus, because if life really is, the origin of life really is, the almost inevitable transition from active geochemistry to biochemistry, then if those conditions have been present long enough on this moon, you might expect for those conditions to have driven complex carbon chemistry here as well. We won't know until we send a spacecraft equipped essentially to fly through these plumes, the ice fountains of Enceladus, take samples and do the experiments and look. But it's a tantalising thought. So I just wanted to give you a sort of brief glimpse of where we are in terms of exploring the solar system. Really, I want to talk about the larger scale, galaxies and the evolution of the universe. This is a very beautiful picture, I think, which was compiled by the European Southern Observatory. And it is of our galaxy, the Milky Way, but from all points around the surface of the Earth. So photographs taken in the northern hemisphere, down across the equator and into the southern hemisphere. From here, in the north, we never see the centre of the galaxy. So the centre of the galaxy is a strip down the middle of this image. We never see it. And the reason is because the Earth's orientation, the solar system's orientation, is such that the southern hemisphere faces towards the galactic centre, and then the northern hemisphere faces out into these sort of backwards of spiral arms, which are over here. So that's why, as you move south down through Africa and then down to the southern hemisphere, the Milky Way gets more spectacular. The reason is, it's not just because of the darkness of the skies. I should say, actually, that one of the great natural resources of Ethiopia, I think, is the darkness of the skies. Chile, in the southern hemisphere, considers its dark skies to be a natural resource. And I think the same is true of areas in East Africa, when you can get away from light pollution and do astronomy. But the reason that, as I said, the reason that the Milky Way looks better in places like Ethiopia is partly because you're pointing more towards the galactic centre and these rich star clouds here. The other interesting thing on this photograph, these two little blobs here, these are the satellite galaxies of the Milky Way. These are called the Magellanic Clouds, small and large Magellanic Cloud. So our galaxy itself is kind of a mini solar system of galaxies, if you like, certainly these two in orbit around it. There are more than 200 billion stars in this galaxy, which is a typically sized galaxy. But we don't see the structure because we're looking at this photographs like this from within the galaxy. So we're seeing sort of a cross-section through our galaxy. To see the structure of the galaxy, we have to look at one of our nearest neighbours. And this is one of our nearest neighbouring galaxies. Visible from here, from the northern hemisphere, it's called the Whirlpool Galaxy. And by nearest neighbour, it's only 23 million light years away, which is why we get these vivid images. This is from the Hubble Space Telescope. It's about the same size as the Milky Way, so about 200 billion stars. It's about, to set the scale for this picture, it's about 100,000 light years across. So that means that light, travelling at 186,000 miles a second, 300,000 kilometres a second, will take about 100,000 years to cross from one spiral arm to the other, which is again the typical size of the galaxy. The blob actually on this side is interesting. That's a smaller galaxy, so-called Whirlpool Galaxy, which is in collision with this galaxy. So this is a gravitational interaction of a very large spiral with a smaller cloud of stars. There's a few 100 million stars perhaps in that cloud, maybe a few billion or so. And you see the distortion of that spiral arm. It's worth thinking, you have to reflect on these things. We're looking here at a distortion, clouds of stars, clouds of hundreds of millions of stars in these spiral arms. So the galaxies, although they're not particularly, they're quite widely separated in the universe. Our nearest neighbouring big galaxy, Andromeda, is 2 million light years away, but you can see it with the naked eye. And in fact, it's about the diameter of the full moon. So even though it's 2 million light years away, by the way, that means the journey began before Homo sapiens emerged in Ethiopia and surrounding countries, and journeyed across the universe. And in the time, well, think about these photons of light. These have been 23 million years in travel time. So when sort of Lucy was taking her steps across the Ethiopian highlands, this light had almost arrived. It's quite a remarkable thought. But even though those galaxies are quite sparsely distributed, they're not so sparsely distributed that they don't interact. So that's one of our nearest neighbours. If we step out again, we start to see the large-scale structure of the universe. And this is a visualisation of real data. It's called the Sloan Digital Sky Survey, which is a project to map the positions of galaxies. So we look into galaxies that we see with our telescopes, we measure the distance to them, estimate the distance, and we measure their coordinates in the sky, and we build up a 3D map of the universe. And that's what this is, it's a fly-through of that data. And the galaxies are represented much larger than they would be. They'd just be sort of sprinkles of dust on this distance scale. But the positions of each galaxy are correct. They are as measured. And so what you see here on this scale is the universe is this sort of snowstorm of galaxies. You see rivers of galaxies and flows of galaxies, clusters of galaxies. If you look carefully, although it does look like a random snowstorm, you start to see there are regions where there are fewer galaxies, or voids in the universe, and regions where there are more galaxies. And this structure is, in fact, it's got a name. It's called the cosmic web. So it's a sort of structure, as I said, described as almost rivers and flows of galaxies crisscrossing the universe. And that is clearly telling us something about how those galaxies formed. So what was it that laid down this pattern that we see in the galaxies, and the pattern of the galaxies across the sky? Well, we have a reasonably good idea. And at the end of this talk, I'll give you our reasonably good idea, our theory as to what laid down that structure. But I suppose the simple message from this is that the universe is very big. In fact, our current estimate, based on surveys like this, for the number of galaxies in the universe is 2 trillion in the observable part of the universe. So 2 trillion items of, 200 billion, 400 billion stars each. So when I said at the start that I think astronomy or cosmology is terrifying in the sense, you see what I mean? When we try to consider our place in this vast cosmos, I think it does raise profound questions about what it means to be, what it means to be human. Cosmology challenges us in that way. So, how can we begin to? I'll turn the light on a little bit so you can see what I'm going to say. So I'm going to do a little explanation, a bit of science here. How can we begin to get a framework, a theoretical framework to begin to understand that? Because it seems absolutely sort of mind-boggling. The theoretical framework actually has its origin in the 20th century. It is Einstein's theory of general relativity, published in 1915. Before that time, there was no science of cosmology because there was no intellectual framework to begin to even have any idea of answering those questions about the distribution of galaxies, where it all came from, and so on. Einstein's theory is, it's a very simple theory to understand, but it has quite profound consequences. And Einstein was driven by thinking about very simple things, such as the nature of the speed of light, the nature of motion, whether it's possible even to define whether you're standing still or moving through the universe. He was driven to reject the notion of absolute space and absolute time. This is back in 1905. And driven to build a new theory or a new picture of what space and time are. And this is a representation of that picture, but it's quite natural. Einstein thought in terms of events. So the building blocks, if you like, of relativity are events that happen. So what's an event? It's something like us getting out of bed in the morning and sitting here now and then wandering off, going for a meal later on, that would be an event, and then going back to our bed later on and falling asleep, that would be an event. They're things that happen in space and time. So they have a location in space and a location in time. So this is a diagram of events. They could be actually the events of my life. So for example, I could have chosen this point here to be the origin of me, like my birth. And then each one of these things is something that happened in my life. So for example, when I'm 5 years old on Christmas Day or something, and that might be when I'm 10 years old and I go on holiday with my parents and so on. So each of those events has a location that we could map out in space and time. And then Einstein's theory has the concept of a slightly evocative concept called a world line, which I've drawn here. So that would be the line that connects all the events in my life, let's say. So let's say that's the event now. I'm somewhere in space, I'm sat here in London, and I'm talking to you. Whatever date it is today, December 28th. I don't even know the date. That's an academic for you, isn't it? December the 6th or something. Anyway, so I connect all the events in my life. Now, Einstein's theory just simply says that what we measure our age, so that the passing of time is the distance along this line. So that literally the time that ticks on our watch. We had a watch when we were born and clicked go, and then it was a perfect watch, and we looked at the watch now, then the time that had passed, which we would call our age, is the distance along this line. Now that has profound consequences. It doesn't seem very radical at the moment, it seems like a simple thing, but it has profound consequences when you think of somebody else and how they would feel and what they would measure. So let's put somebody else's world line on here. Let's say that one. Let's say that could be my mum's world line, for example. The reason I say my mum is because obviously we were both present at this event. But then she would have done different things to me. I didn't spend up my whole life stood next to my mum, so she would have gone to different places, she might have travelled to different countries or whatever it is. So she will have a different path over space and time between any two given events. So let's say that's when I come back, let's say that's Christmas Day this year when I go and have Christmas dinner with my mum, so we're in the same place at the same time. But because we took different paths through space and time, her watch, which measures the distance along this line, will measure a different time to mine. So once you define your watch, once you define time as being a measure of the distance that you've travelled between events, then it turns out the notion of absolute time doesn't make any sense, because everyone measures a different time between events because they take different paths. That's not particularly radical. Of course, if we decided to travel to Addis Ababa and we went different ways, we travel different distances. Well, it's exactly the same here, except we've got space and time merged together. And that's one of the key foundations of Einstein's theory of relativity. And it's quite strange. It means that people age at different times. Quite literally, your time is personal to you. So you travel a different path through the universe, you will age at different rates to anybody else. Profoundly interesting and unusual. Now, Einstein took that picture of space and time and turned it first into a theory of gravitation, a theory of gravity. How did he do that? Well, he was thinking about very simple things initially. And this is, again, I think, quite an interesting lesson about how you do science and being curious about the nature. What was special about Einstein? Not much, really. I mean, he always said, actually, I was talking to him earlier about Einstein. He went to some schools later in life when he was very famous scientist, a great genius. And he was asked a question, and he said to one of the students, you know, when I was your age, I was no Einstein. I was just like you. Einstein, one of the things that's special about Einstein was he got interested in things that seem obvious and trivial to most people. It's very easy for us to dismiss the behaviour of the universe, observations of nature, just saying, well, yeah, it's not that interesting. But there's real depth in thinking very carefully about why things happen in the way that they do. I'd just like to show you this, which is something that we filmed again for a television series, actually the same series, where one of the ones that I filmed in Addis. It was filming the behaviour of objects falling in gravitational fields. In this case, a very famous experiment of feathers and bowling balls. So we did this in the largest vacuum chamber in the world, which is in Ohio, actually. And it's NASA's spacecraft. It's called the Spaceflight Power Facility, actually. But it's where NASA tests spacecraft in a vacuum before they send them into space. When we watch things fall on the surface of the Earth, we're seeing two things. It's quite complicated. We're seeing their response to the gravitational force, but we're also seeing air resistance and all sorts of really complicated things. But if you pump the air out and watch what happens when you drop things in the gravitational field, you see gravity in its pure form. And so that's what we did here. Now, we've sort of all probably know the answer to this, But what happens when you drop two very different things and they accelerate down to the ground under the influence of gravity? In this case, a feather and a bowling ball. Well, obviously we did it in here. The bowling ball would crash to the ground and the feather would float gently to the ground. You take the air away though, and you film this. So this is a real experiment that we did, and you film it with ultra high speed photography. Then you see what gravity actually does when you take everything else away. And it looks weird, right? That's what gravity does. Now we all learn that at school, things fall at the same rate in a gravitational field. But it still looks odd when you see it. And actually when we did this, I said that's slowed down, this is ultra high speed photography. So you can see that as Galileo knew, they hit the ground at the same time. When we did this, by the way, the NASA engineers round of applause. and then we realised that you can't really applaud the law of nature. That's the way the universe behaves. Now, what Einstein was interested in is why. And actually, in Newton's laws, going back to the 1600s, there isn't an explanation of why that happens. The actual behaviour is encoded into Newton's theory of gravity and Newton's laws of motion. But it's encoded in because it is. Now Einstein was not happy with that. He felt that was kind of I suppose avoiding the real issue. Why would it be? That's a really strange behaviour. And when Einstein came up with it, using this picture of space and time that we spoke about, these events sort of scattered through this sort of space-time diagram that I showed on the previous slide, what Einstein realised was that if you have that picture of space and time with all the events in it, you could consider it as, and it's often described as a sort of fabric of universe. So we don't think of space as a big arena in which things happen and time that just ticks along on a big universal clock in the sky. That's not right. That's not the way nature is. But you can treat that structure of events, if you like, a set of all things that happen, as sort of a fabric. And Einstein realised that if you assume, or you postulate, that when you put massive objects into that fabric, in this case the Earth, then it distorts the fabric of the universe, it distorts space and time. You get a geometric picture of what gravity is. So Einstein's idea or description of what happens, let's say the moon orbiting around the Earth, Einstein's description of what's happening there is just like rolling a little marble around on this surface. What would happen if you did that? You roll the little marble around here, it wouldn't go in a straight line past the Earth, it would be deflected, because the Earth is the fabric of the universe. And in fact, what you find in Einstein's theory is if you calculate that distortion and roll something around, then it can go into orbit, and that's what an orbit is. So an orbit is an object like the moon following a straight line through the curved space-time, and the space-time is curved by the Earth, and that's an explanation for what the force of gravity is. And now perhaps you can see how this theory is rather good at saying why things behave in the same way under the gravitational force. They do that because the gravitational force is nothing to do with them at all. It's their response, it's their movement through the curved space that we're seeing. And so in that sense, it's pretty obvious that a feather and a bowling ball will behave in the same way, because the motion has got nothing to do with them at all. What they're doing is feeling the curvature and the warping of space and time caused by the mass of the Earth. So that's Einstein's theory of gravity. It's a beautiful thing, and it works very well. So one of the first things Einstein did was calculate the orbit of Mercury around the Sun, and he got a better description of the orbit of planet Mercury around the Sun than Newton. So whatever you do with this, it is a better model of gravity. But then, shortly afterwards, this model of gravity became a model of cosmology, a framework for describing the evolution of the universe. How do we do that? Well, I should just say before I say that, do we have any, I said that we could predict the orbits of Mercury. Let me just show you one other piece of evidence that tells us this picture, the distortion of space and time is a good one. So this is a real photograph. It's a photograph of a cluster of galaxies of Abel 2218. It's a big cluster, 1,000 galaxies or so, in the foreground of this picture. And then in the background there are other distant stars and galaxies. It's about 2 billion light years away, this cluster of galaxies. But you can imagine, as I said, a galaxy's got 200 billion stars in it, and there are 1,000 galaxies or so in that cluster. That's a whole lot of mass. So it's doing a lot of distorting of space and time. What you see in this picture is a really weird sort of structure, these arcs all over the picture. And again, this is a Hubble Space Telescope photograph, so it's not really manipulated or anything like Photoshop, just a photograph of the sky. What are those arcs? Well, those arcs are images of the distant galaxies, the distant stars. So what you're seeing here is the light from the distant stars coming towards us through the cluster of galaxies, which is distorting space and time, and so it's distorting the image of the background stars. So this is almost like looking at something through a wine glass, but the wine glass is the distortion of space and time itself. And you see these characteristic arcs, which are known as Einstein Rings, which are predicted by the theory, but predicted way back in 1915. By the way, in 1915, we didn't even know there were galaxies beyond the Milky Way. So Einstein didn't know this, but his theory predicts it, and you see it so vividly in this photograph. Now, I just show you just for fun. Someone mentioned that I was doing these big cosmology shows next year. So one of the things you can do when you've got a big audience coming to see your shows is you can spend lots of money on graphics. Use their money to do cool things. And I just want to show you this because it's a simulation of what it would look like to fly towards a black hole. Now, a black hole is a completely collapsed star. So many times the mass of our sun that's collapsed essentially to, as far as we know, an infinitely dense point. So nothing can, as far as we know, can hold the star up. If it runs out of fuel in its core, there's nothing to stop it collapsing under the force of gravity. So it collapses to something that's incredibly dense. That means that space and time around them are incredibly distorted. And what we can use Einstein's theory to predict that distortion, as we saw in the previous photograph, and we can watch what happens if you fly towards it. So this is, I'll turn the lights down so you can see it. This is our best guess, or our best prediction of what it will look like. So the black hole's in the middle there, and it's got a disk of material around it, which is called an accretion disk. That's what happens. So material spiraling around the gravitational field of the black hole. And all that strange distortion background as we fly across the black hole is the prediction of Einstein's theory. And it's the distortion of space and time. And you see as we approach it and get closer and closer, the distortion gets more and more radical. What we know is that as you approach a black hole and fly across it, so this is us flying across it, time will be so distorted that we will age significantly slower than anybody that's sat a long way from the black hole watching. And by significantly slower, I mean years and years and years. So it's possible, as far as we know, spin that around and carry on the orbit. So it would be possible to go into orbit around the black hole and sit there for, let's say, a year, and then emerge out again. And such is the distortion of space and time that 100 years, or 200 years, or 300 years could have passed outside, in fact 10,000 years. So in that sense, a black hole can be like a time machine that can propel you into the future, as far as Einstein's theory is concerned, not to the past. We think that Einstein's theory protects the past from the future, which is a rather good thing. But this distortion of space and time certainly allows, as far as we know, for an astronaut to go into orbit and come out indefinitely, essentially, far into the future. So it's a very strange theory indeed. Now, what does that have to do with cosmology? Well, how does a theory of gravity fit a theory of the universe? It was essentially in the hands of 2 or 3 people, Einstein himself. And I like this picture of Einstein. Again, I was talking to someone earlier. The picture of a scientist often, especially if he goes to a group of children in school, is often usually an old man. Let's face it, which is not a great image if we want to encourage particularly young girls, but also young boys to go into science. It's not true. It's true that science was quite male-dominated, of course, in these times, but it was a young person's game. And actually, Einstein looked rather more like this. He was in his 20s when he was building these theories. He was not in his 50s and 60s. So he was quite a handsome and interesting young man at the time. And this is 1915 or so. Because Einstein, there was a man called Alexander Friedman, who actually did some of this work whilst he was fighting in the First World War. and in fact contracted TB and died not long afterwards. So he was doing some of these calculations in an artillery, he was an artillery calculator for artillery guns in the First World War on the Russian front. And then this man, Georges Lemaitre, who, as you can see, is a priest, he's a Belgian priest. An interesting man, a poetic man. He was once asked, how is it that you can be a priest and a mathematician and a physicist at the same time? And he said, there are two roads to the truth, and I choose to take them both. These three individuals working with Einstein's theory all realised roughly the same thing at the same time, around 1918, 1920 or so. They realised that, see, what does Einstein's theory do? It says, well, if I put a blob of mass into the fabric of the universe, like the Earth or the Sun, then it tells me the shape of space and time around that thing. So it allows me, for example, to calculate what will be happening, let's say, to solar system and planets going around the star. It allows me to calculate what would happen in the past. So I can run the theory back and see what happened in the past. Or I can run the theory forward and see where the planets are going to be in the future. These three realised that, or had the idea, could you do that for the entire universe? Could you put the distribution of matter, stars and galaxies and so on, into Einstein's equations and crank the handle and come out with a picture of the past, present and future of the entire universe rather than just the solar system? It's an audacious thing to do, and there's no reason to believe that the theory would stand that challenge. In fact, Einstein wrote to a friend of his when he was thinking of doing this, he said, I'm about to try something that might seem inside to a madhouse. So he was kind of reluctant. But they all did it. Now, you might say, well, how do you know the matter distribution of the universe? That's a crazy thing. They didn't, but they made a simplified assumption, which is good science. They said, well, let's assume the universe is the same everywhere on the largest scales, the ultimate Copernican principle. So you assume that matter is distributed on large scales completely uniformly. And if you do that, such is the simplification in the theory that you can calculate what happens to the universe. And what they found is that in almost all models, very simply, if you just stick matter into the universe, it tends to stretch. The fabric of the universe doesn't just distort, it tends to stretch. And Lemaitre in particular, and I find this very interesting from a sort of sociological perspective, or human perspective, Lemaitre in particular thought, well, if the theory suggested that in general, you stick a load of galaxies into the universe, then the fabric tends to stretch, then that means that in the past, everything must have been a bit closer together. So you can imagine if it's stretching today, then you wind time backwards, everything must get a bit closer. And that sort of seems to suggest that everything at some point in the past must have been very close together, so almost on top of each other. And he wrote to Einstein and said, your theory suggests there was a day without yesterday, which I think is a very beautiful sort of letter to write. Your theory suggests there was a day without yesterday. Because he's imagining that that time when everything was on top of each other could have been the origin of the universe, which is what today we call the Big Bang. But it's coming primarily from the theory, not observation at the time. And Einstein wrote back to him and said, your mathematics is excellent, but your physics is lousy. Because Einstein didn't like it. Einstein, I think, was more comfortable with an eternal universe. Because then you don't have to face the idea that it had a beginning, a creation event. And therefore, I think in Lemaitre's mind, a creator. So it's sort of interesting to me that a priest is more likely to accept this theoretical prediction, at least initially, I think, because it confirmed his pre-existing view of the universe, which is something that had a beginning. And it turns out that that's right. The universe is expanding. We observed that in the late 1920s, not long after the prediction. And actually Einstein soon came to accept that Lemaitre's maths was correct and his physical intuition was correct on the universe. That is essentially this one, which is a schematic picture of the evolution of the universe as we know it today. So because we can measure the expansion rate, we do that quite simply by looking at the light from distant galaxies and noting that it's stretched. So if you look at a galaxy, say 1 billion light years away, you notice that the light, the colour of the light is stretched. So light of a longer wavelength goes red. This is called a red shift. And we also notice that the further away you look, the more the light is stretched. And that's a very simple observation, because the light is travelling across the universe, but longer for the galaxy that's further away, its light would be more stretched, like the expansion of the universe. And we can measure this. So we can map out the expansion rate. That's what allows us to estimate the age of the universe back to the Big Bang. Because if we know the expansion rate at lots of different times, then we can run time backwards as Lemaitre in his mind's eye and say, well, is everything on top of each other? And that's where we get these numbers, 13.8 billion years for the age of the universe since the Big Bang. It's observational plus Einstein's model, which comes from his theory of gravity. Now, there's one more, if I'll take questions in a minute, there's one more thing I want to say. These things are, of course, theoretical predictions, although we do observe a stretch of the light. There's one other key piece of evidence, which is very beautiful, which was the clinching idea that there was a time in the history of the universe when it was very hot and very dense, the Big Bang. And that was found first in the 1960s. But the idea is quite simple. I mentioned the Whirlpool Galaxy we looked at earlier. So I said, here's a thing, it's 23 million light years away. So we see it as it was 23 million years in the past, because it's taken the light 23 million years to journey across the universe to the Hubble Space Telescope. I can imagine human evolution taking place as that light journeyed across the universe. So you might say, well, if that's the case, then would it be possible to look so far away that I see things so far back in time that I can see the origin of the universe? Can I see the light from here at a time before there were stars and galaxies that's travelled across the universe for 13.8 billion years? And the answer is yes, actually, you can. And this is the photograph of it. It's a photograph taken by a satellite called Planck, a European satellite, which sits there and observes the whole sky. So that's why it's a sphere, because it's sort of like the celestial sphere, if you like. The spacecraft can do that, all points in the sky. So this is essentially looking as far out into the universe as you can see in every direction from the Earth. And you do indeed see a time when there are no stars or no galaxies, but you see a time when there's just a uniform glow in the sky, which is this. It's called the cosmic microwave background radiation. So it is the afterglow of the Big Bang. And this was first seen in the 1960s. A Nobel Prize was awarded. It was actually discovered by a telescope that wasn't designed to look for the cosmic microwave background radiation. It was a microwave telescope looking for other things. And in fact, Penzias and Wilson, who got the Nobel Prize for it in the 60s, the discovery, thought that this background hum they were seeing in the telescope was pigeon droppings on the telescope. So they got in there, cleaned all the pigeon droppings off and still saw the hum. And then it was realised that in fact, these Big Bang models of cosmology predicts there should be a hum, which should be the afterglow of the Big Bang light coming at us from the most distant parts of the universe. And this is it. And these days, this is a modern picture, we see not only a uniform glow, but a thing with structure. These different colours correspond to areas of different density in the very early universe. Just a few 100,000 years after the universe began. That's where this light came from. So it's almost smooth to 1 part in 100,000. So it's almost a glowing mass of matter before the stars and galaxies form, except for these little islands, essentially, with different density. And what we think happened, or we know happened, is as the universe expanded and cooled from this point, the areas that were slightly over-dense got a bit denser and a bit denser relative to the other bits until they collapsed from the first stars and galaxies. So these things, when George Smoot got the Nobel Prize in the 1990s for discovering these sort of different variations in the young universe, he said that these images were like looking at the face of God, which is an interesting way of putting it. He's not a religious man, actually, George Smoot, but he's right. What he was saying was these little fluctuations in the young universe are the origin, they're the seeds of our creation, in a sense. Because without them, if this had been completely smooth, there would have been no stars and galaxies. We'd live in a completely uniform universe, and we wouldn't be here. So this is extremely important to understand where this pattern came from. What we do know is if you run this forward in time in our simulations, you get a distribution of galaxies in the sky that looks very much like the distribution of galaxies we see today. So we're pretty sure this is where the galaxies came from. very briefly, finally, because you will be asking us, well, where did they come from then? This is so important. The theory of where these come from is quite stunning. It's called inflation, and it's the cutting edge of modern cosmology. So the idea, very briefly, is that our universe, before it was hot and dense, so before the Big Bang, it was still there, and it was expanding extremely fast. It was cold and empty and stretching extremely fast. And what that allows us to do is, with our current understanding of Einstein's theory and also quantum theory, which is our theory of the subatomic world, if you like, our theory of everything else in fact other than gravity, it allows us to trace back to a time when our entire observable universe, 2 trillion galaxies, was compressed into something smaller than the nucleus of an atom. A little tiny patch of space, which is going to expand very fast, and then that very fast expansion draws to a close, and the universe, sort of, all the energy that was driving that expansion sort of collapses into space, and heats it up and makes particles, and that's what we call the Big Bang. And we can calculate all the way through that. Now, when our entire universe, all 2 trillion galaxies, was something smaller than an atom, quantum theory rules. And quantum theory tells us that there's always little things fluctuating in and out of existence on a very subatomic scale. So space is a physical mass of stuff at these tiny, tiny subatomic scales. And we think that that rapid expansion grabbed those little fluctuations, tore them apart, made them real essentially, and wrote them across the sky. And that's what you're seeing here. So, and when we calculate that, we get the right answer. So we think that the galaxies, the distribution of all that stuff we see in the universe, has its origin in a time when our universe is subatomic in size and fizzing and fluctuating around. And those little subatomic fluctuations are written across the sky by the expansion. And so that's what we're seeing here. We're seeing quantum mechanics written across cosmic scales, and we get the right answer. So that's a remarkable thing. Then I'll leave you with that thought. I think it's quite, this is 100 years of science, but that's all. Just a little window of 100 years, going from 1915 and our first theoretical glimpse at how we might describe the universe, to a theory that we developed that can explain the structures that we see in the universe today. Still doesn't explain what happened at the beginning, doesn't even explain whether there was a beginning to the universe. All we know is that 13.8 billion years ago it was very hot and very dense, because we've got a photograph of it. But we don't know when the inflation time started before the Big Bang. We don't know if that's eternal. We don't know if time had a beginning. And we don't have a theoretical framework for understanding how we might start to address that idea of what would the beginning of the universe mean. So we might live in an eternal universe for all we know. But it's an exciting time in cosmology because of this precision data that we have now that we want to explain. So with that, I'll say thank you very much for listening. And if there's any questions, I can take. Thank you. Well, there's one there. I think you can shout out, or there's a microphone.
So, hi, Mr. I first got interested in physics when I was about probably 3 or 4 years old, watching Space 1999.
Yes, I love that series.
On Ethiopian television, and then when I moved to the UK, I watched Star Trek for most of my teenage years. I studied at the University of Manchester. I studied physics. Professor Jeff Forshaw, who you've written with quite extensively. Professor Fred Logan was the one who got me into the University of Manchester.
Yes,
same
for me.
Yeah, those two are, and I played for Physics Football Club, which...
So did I.
So did Professor Jeff Forshaw. I think those two lecturers that I mentioned were very inspirational. Professor Jeff Washer taught us quantum physics and relativity, and Fred Overgate taught us cosmology and astronomy, which we've pretty much put 3 years of my studies in like 1 hour. How do we get physics lecturers to be that inspirational, to be grabbing the audience? How do we get it on TV like you have done within Africa? How do we get it to the masses? How do we capture their imagination?
It's a good question. I think about 10 years ago, the BBC, which is, we all know, it's an institution, a national publicly funded institution, whose job, as I sometimes have to remind them, is to act in the interest of the country, to make it better, and not just compete with I'm a celebrity, get me out of it. What they did 10 years ago, in particular, was they had a time when they deliberately took young academics and put them on television. And there's a lot of people who came out of that decision, so as myself, people like, you might know Professor Alex Roberts, and Ian Stewart, and Helen Chersky and Maggie Daring-Pocock, and lots of people who are kind of, to a greater or lesser extent, public names, who then use that platform. And I think that's really important. I don't think they're doing it as well as they should now, actually, because, but that idea that a public broadcaster can take its responsibility seriously and can be used to bring young academics from all disciplines through to the attention of the public and create a critical mass of people who can practice and are interested in speaking. That's one component. And the other component is that universities, and I've been very lucky in this respect, partly because I was funded as a research fellow by the Royal Society to take this very seriously here in Britain, but I was lucky to be given the space to do it. So there's two things. You need a platform which you can have if you have a broadcaster that plays ball, essentially. And there are, I know that those exist in Africa and across the world. And secondly, you need universities that allow the academics that choose to do that to have the time to develop that important part of their career. So in Manchester, we used to have this thing, it was a terrible idea called the three-legged stool, we called it, which was for promotion. How do you get promoted in the university? And it was an admin, teaching and research. And now we have admin, teaching, research, and we call it social responsibility. So it doesn't have to be giving public lectures, it can be being engaged in the community or whatever it is. But that now is considered to be an equal part of the 4 parts of an academic career. And that's also important, because then you don't put people off. If you're a postdoc, it's quite a bold step to spend some of my time, 10% of my time or whatever, being engaged in the community or through the media or whatever it is. So you know that that's considered to be a valuable part of your career, that's also important. Okay, we go there, and then we have to go over there. You always get the edges. We'll go.
Hi, thank you very much for the presentation. My name is Aminette and I'm a GKEN member. I'm interested in horology, the study of time in African indigenous knowledge systems, and I've got 2 questions. The first one is, in relation to the description of a black hole, could you explain what the event horizon is? And secondly, what is your view of Dogon cosmology as part of African indigenous knowledge systems and the contribution to science? The Dogons of Mali?
Yes, I don't know much about, perhaps you can tell me, but I'll answer the first question, which is the event horizon of a black hole. In fact, I put this spinning view of the black hole. So on this picture, the event horizon is actually on this simulation, it's this line here. So if you think about what a black hole is, it's essentially, we know, an infinitely dense spot of matter. So there's an area around that where if you sent a light beam out from within that area, then it wouldn't ever be able to escape. So it would just circulate or just, in fact, stop on the event horizon. So the event horizon is the area around the black hole from which nothing can escape. And if you cross it, then you are forever doomed to, well, not forever doomed actually, you are very quickly doomed to go and hit the singularity at the centre of the black hole. So it's a simple idea. It's a region around which, because the gravity is so strong, or because the space and time is so curved, that once you cross the event horizon, you can't get out of it. And in fact, there's a very interesting thing that happens in theory, which is that essentially the time, one way of thinking about it is the time and space component sort of swap around on the horizon. So we know that what we have to do is, one of the tragedies of human existence, I suppose, is that we have to march inexorably into the future. So we can't stop our motion forward in time across space-time. Well, when you go across the event horizon of a black hole, the future is the centre of the black hole. So you are going to be squashed to an infinitely, you're going to meet the infinitely dense point in the same way that we are going to meet tomorrow. And that's what happens when you cross the event horizon of the black hole. I don't know about the cosmology question, so maybe we can have a quick chat afterwards, because I find it interesting. Should we go right over there, we'll go right over to the other side of the room. Do tell me when you want me to. I suppose it's lunchtime at some point, isn't it? So I will stop whenever you want me to.
My question is, in terms of your English and Einstein's theory, what do you think will happen to the universe, like in the future? Do you think it will just continue expanding?
That's a really good question. The question is, what will happen to the universe in the future? If I show you this diagram again, which is there. So this is. There are some features of this. It's got all of our knowledge in it at the moment. I didn't talk about it all. But in particular, there's this bit here. It's this dark energy accelerated expansion. So what we found is a friend of mine actually got the Nobel Prize for this in the 1990s, called Brian Schmidt. And he was a postdoc. It's a good lesson actually to research. He was a postdoc who was looking at the stretch of the light from distant objects. In this case, supernova explosions, which are very bright, so you can see them a long way away. And he was measuring it. And he found that the stretch of the light he was measuring suggested the universe is accelerating in its expansion, not slowing down, but actually speeding up. The space is stretching faster and faster. And he thought that he'd done something wrong, because nobody expected that. But he checked everything, and he thought, well, no, I can't see anything wrong with it. And he said to us, I saw him give a talk where he thought, I'll publish it, but that's the end of my career, because it's obviously nonsense, but I can't find anything wrong with it. And he got the Nobel Prize. So we're pretty sure, and it's been that this has been confirmed by many other measurements, that the universe is accelerating. So that means if it carries on doing what we measure it to be doing now, and nothing else happens, then it will get to a point, we think, where it just keeps doubling in size forever. And it doubles in size every 20 billion years or so. So we think the future of the universe is that it will be eternal, so it won't sort of slow down and relapse or something like that. And it will just get to this point where it's an exponential expansion, it just keeps doubling and doubling and doubling. And that ultimately means that all galaxies initially disappear away from each other such that you can't see them. So from any single galaxy, you can't see anything else. So there will be no bright galaxies across the universe. And in fact, ultimately, we think the galaxies themselves evaporate away. And so we end up in a universe with nothing at all, no structure, which is sort of, I don't know, it sounds like a rather miserable future for the universe. It's called the heat death of the universe, where there are no stars and no planets and no galaxies, and just darkness. So that appears to be what we think the universe will do. Just to say, it's possible. We don't know what this is. We don't know what's causing that expansion. We know exactly how much energy we need, because Einstein's theory allows us to calculate what's in there to make the universe stretch. But we don't know what it is. So it could be that it can change its form somehow. And that might change the evolution of the universe. It may mean the universe will collapse. So this is one of the central questions in modern cosmology. Is what actually is stuff we've called dark energy. 70%, by the way, of the energy in the universe is taken up driving that expansion, but we actually don't know what it is. So there's a couple more, I guess.
Can I just make a proposal before we go on? This is
fascinating.
We better run it.
We have, but I think if you don't mind, I'm going to make a proposal that we continue to 1 o'clock with questions and then we take a break. And we have a slightly shorter lunch, if that's okay, just so that we can accommodate the next speaker. So please do
I'm happy to
continue
get through to the
1
5 minutes.
o'clock.
So who wants to choose? Someone really wants to ask a question right at the other side of the room. So when you do that, then someone else can choose, because I feel bad. Got right with that. I'll try and speed up as well if I get to
Oh, very simple question. How do you reconcile Stephen Hawking's radiation from a black hole with the gravitational distortion that you're talking about?
Yeah, well, it's not only to reconcile them, it's actually, so one of the things Stephen Hawking is most famous for in physics is something called Hawking radiation, which is the idea that these things, I said nothing can escape from a black hole, that's what the event horizon is. But actually, it turns out that that's not quite right as far as we understand. The black hole evaporates away. So how can a black hole evaporate when nothing can escape from it? I mean, that's an interesting thing. Hawking radiation, he noticed that, so I mentioned very briefly quantum theory, and I said that quantum theory tells us that on short distance scales, subatomic size scales, then everything is fizzing all the time. So really, one of the things I mean by that is that we know, as we observe it, that particles can pop in and out of existence in pairs. So for example, an electron and an antimatter electron can pop into existence and then they disappear again and come back together. So you can borrow energy, essentially, from empty space for a short period of time, as long as you give it back again. So the reason I said electron and antimatter electron is that we know that you can't create electric charge out of nothing, for example. So if we're going to make a negatively charged thing, like an electron, we better make an equal and opposite positively charged thing, which is an antimatter electron. So we don't violate any of the laws of nature, so that can happen, and they come back and disappear again. And we actually see the effects of that all the time. So empty space is full of this, so we can measure it. So we know that happens. What Hawking said was, what happens if that happens on the event horizon of a black hole, very close to it? It is happening, we're sure it's happening. What can happen is one of them can wander across the event horizon, and the other one can stay out in the space where it's free to escape. And they can't get back together to meet again. So what happens? Well, one of them falls into the black hole, and the other one becomes real and travels off. And that takes energy away from the black hole, essentially coming from the gravitational field of the black hole. So by that mechanism, we think that black holes can radiate, essentially by making what physicists would say is quantum fluctuation, wheel. And the energy's got to come from somewhere. So it comes from the black hole, and so it evaporates away. And you can calculate, so that gives a black hole a temperature, which allows it to be an object that we understand in the universe, the temperature, so it radiates and so on. If you calculate what the temperature is of a black hole, let's say the mass of the sun, it is extremely low indeed. So the radiation is an extremely slow evaporation process. And if I remember rightly, it's roughly, I think if you calculate how long it would take for a black hole the mass of the sun to evaporate, it's something like 10 to the power 67 years. So that's one with 60 or 65, 67 noughts after it. And now the universe at the moment is 10 to the 10 years old, right? 1 in 10 noughts. So if you think what 1 in 60 noughts looks like, it is, well, a lot older than the age of the universe now. But we think that's fundamental. So it's one of the parts of our fundamental understanding of these objects is that they participate in the laws of nature, they have a temperature, they radiate and so on, in the same way that it does. So that's one of Stephen's great contributions.
Unfortunately, I think we really do have to take the last question now. I think it's very unfortunate.
I think it's on the microphone, sorry.
I was wondering, since the galaxy has a Whirlpool type shape, does that suggest that there's a black hole in the very center of the galaxy? And if so, does that mean that the creation of the galaxy is due to this black hole?
So the question is it's actually another fundamental question about galaxies. So I thought the last thing I put up is go back to my galaxy. Go back to the Whirlpool Galaxy. Spectacular thing. So we know that most galaxies, I think all galaxies, have a black hole at the centre. And some of these are supermassive black holes. So we're talking about millions and millions of times the mass of the Sun, hundreds of millions of times the mass of the Sun. So one of the fundamental questions, which actually, one of the big Southern Hemisphere projects, the Square Kilometre Array, which is being built in South Africa and Australia, so a big radio telescope. One of the things that that's designed to do is to look back into the era when the first galaxies are forming, to start to address these questions. What happened? What forms first? I think one of the possibilities that many astronomers think likely right, but we need to see, is that enormous stars form first. So really, hundreds of times the mass of the Sun, big stars, and then they burn very quickly and collapse into black holes. And that may be performing a role in the evolution and origin of the first galaxies. But it's really cutting edge astronomy actually. And we have the ability now to begin to look so far away with such detail that we can see the formation of the first galaxies, so we can check. But it's a fundamental question. But it is true that every galaxy, I would say, has a black hole. The Milky Way has one. It's not actually that massive. I can't remember off the top of my head how massive it is, but it's only millions of times the mass of the Sun, and not much more than that. I can't remember exactly what the number is, but yeah, it's a good question.
Thank you very much.
It has been exceptionally educational, and I'm sure that triggered so many questions for those of us who never managed to understand what universe means. Therefore, thank you very much, Mr. Ray, Brian. We are extremely grateful for your excellent lecture, and I'm sure this will be the first of many to come up. And obviously, as GKEN, we are extremely actually humbled actually to have Brian as our member. That by itself is, I think, for us from GKEN, that's a great achievement, because this is a kind of individuals who are attracting, which is actually a beautiful thing to do. And on top of that, Brian also kindly have agreed to act as our patron to GKEN. Therefore, I'm sure all of us will have learned quite a lot, but this kind of things are likely to continue more. As you also know, most importantly, the topic we chose for this particular symposium was popularizing science in Africa. Therefore, for those of us who have an interest in Africa, similar to Brian, I'm sure we'll take that message away. And of course, the lectures today, purely focusing on exploring the universe, also have been an extremely learning curve. I think with this, we'll have a break, a line to break. And once again, let us give a really good round of applause.